Oh, Noel. Oh, Noel.
Alrighty.
I think I'm like a dad in my past life. Too many dad jokes.
All right, welcome back. Happy Monday. Good to see you again. Last week before spring break, crazy. We're gonna try. We'll see how it plays out. We're just gonna go day by day, but we're gonna try to finish Unit 2 this week. We're almost there, and I think that a lot of the conversations that we're gonna have today are gonna lead us to that spot. So I feel really good about where we finished in second period. Hopefully, kind of get into that same spot today. Bouncing around a little bit and skipping stuff for the sake of time, but also for the sake of like continuity in your brain of how things connect and getting to the good stuff. But quickly backing up to Friday or this weekend, if you worked on it this weekend, how did this go? Okay, this all right? The whole limit definition, and we're kind of working through this stuff really quickly. Now you don't have to really start making like super obvious, or not obvious, super. What's the word I'm thinking of? I don't know. I lost it. So let me rephrase. I don't think it's super critical that you see all of the connections yet between the function and the derivative, like calling this x to the 1/2 and noticing that this is 1/2 x to the negative 1/2. Like not necessarily catching on to that yet. But what I do want you to start realizing is that although a lot of times with these square roots we have that 1/2, but that one doesn't have it, right? That is just 2x minus 1 to the negative 1/2. And the 1/2 is not necessarily there in our final answer, which means that like what's underneath the radical has to play some role. It's not just x, so there has to be something going on there. But the more kind of connections you start to see, I think the easier this transition tomorrow, I think it's tomorrow, where we actually get our hands on the shortcut, or at least start to put the pieces together, starts to come into play. And so maybe another thing to kind of peek at is, do you notice anything about the rational ones? So look at the function, look at the derivative. Do you notice any patterns like the radical ones are like 1 versus 2, like f of x versus g of x? This one is more about like just looking at 3 and 4 together and seeing if you notice anything that stands out. Is there anything about r of x compared to r prime of x that you also notice y to y prime? Do you see any connections? Do you notice anything? That's true for both. As you make the leap from the function to the derivative. Aiden, what do you see? Nice. The denominator stays the same and then just gets squared. The denominator stays the same. Look, so x minus 1, okay, x minus 1 squared. X plus 3 squared. Awesome. You're absolutely right. And you're going to see that when we get to chapter 3, and we start looking at quotients. Okay, there's actually a rule that goes with derivatives for quotients where we can skip all this limit stuff. And I don't know, like you tell me, do you feel like you get it? Like, okay, there's a limit derivative, like there's a definition for the limits, and it works. And you feel confident that if things work, that you can just do them. And that's what I want to start getting away from. Like, you get it. Awesome. Like, that's not the calculus. That's the beginning of calculus. Calculus is about finding ways to be way more efficient than doing things the long way. And so that's what we're going to be building to over these next couple of days. But noticing that there's like connections between how things start and where things end, and realizing that, if we've got more going on than just x, that it's going to play a role in this whole process. But we will be able to do all of those derivatives very, very quickly, very, very soon. And so in order to do that, I think it's important that we kind of keep rolling on here and jumping back into our guided notes, I think is going to help us. But what I want you to know is okay, is that I know we've bounced around a lot and we've skipped a little bit, and we're going to continue to do that. I think we filled out a majority of the beginning, right? We did like all of page 115, all of page 116, where we started to get into the equation of the tangent lines a little bit. And I know that that kind of happened briefly. We didn't do a ton of that, but y minus y1 equals mx minus x1, right? All I need is the point and the slope. The point comes from the function and the slope is the derivative. And that's all I really need, right? Because when we say derivative, we think slope of the tangent line and vice versa. And sure, we've got this super long way, but my goodness, I don't want to keep doing it the long way as long as I can. And so at this point, I'm really, really starting to be done with that. And so we're actually going to skip all of this sideways page here on 119. But I just wanted to point out that, like, I know we've talked about, like, the distance between the points going to 0, right? H went from 3 to 2 to 1 to, you know, we're just, like, making that distance between those points smaller. I can write that by saying, okay, like, here's a point X, here's a point, you know, A. Let's move those closer together. So there's two different ways to write them down, but they're the same. It's just two limits, and then we just make them go together. So don't sweat any of that stuff, 119, 120. It's just a different way of thinking about it, but it's very rare that we would use that setup. 121, we did a lot of that. 122, I know we didn't quite get all the way through, but the idea of saying, okay, I can find the derivative, which means I can find the slope of the tangent line. And if I've got the slope, I can do anything. That's kind of where we're leading to. Okay, and so we're actually going to start today on page 123. Okay. So if you've been just kind of flipping through, go ahead and get yourself stopped comfortably at this page right here. And what I want to start doing is starting to make some more kind of overarching conclusions about, okay, like, what is the derivative? What's the slope of the tangent line? Tell me about the function itself as we put things together. We're going to start making those connections. Okay. And so you've got this nice smooth polynomial, whatever it is, some cubic upside down looking thing, or some top degree 4, because arrows point in the same direction. And what they want us to do is kind of stop along the way at a bunch of different spots, right? -7, -6, -4, and so on, and get a sense for what we think the derivative might be at those spots. Okay. And so the best way, I think, to do that is to try to estimate the tangent line. Now, before I get that going and we actually start drawing out some tangent lines, I want to put some ideas in the back of your mind for those of us that want a better way to think about how to make this easier, how to understand what the derivative in the function is going to do. And so I'm going to say this in a lot of different ways, but it all comes down to being able to understand that because we read English from left to right, we're going to read graphs from left to right. You don't have to draw that arrow, but that's how I want you to think. And calculus is about movement and study of change, and we are going to move ourselves along this function from left to right. And when they say, hey, stop at -7, or stop at -6, or stop at -4, or whatever it is, that although, yes, we're going to stop and see what happens, the motion didn't stop. We're just taking a snapshot of that motion and trying to figure out what's happening. So I think the more you can wrap your heads around the idea that this graph represents movements, I think it'll help you understand what we're talking about. And so the analogies that I've tried to put in the back of your minds, and you find the one that works best for you, is like rolling a ball up and down this hill. Or, I don't know, like, actually, like, you know, like walking along that hill. Okay? And when we think about movements, like, so I'm like looking at like me like climbing a mountain from the side and looking at like elevation change as I go and thinking about, what am I doing? Am I going up? Am I going down? Or am I at a point where I've reached like the top or the bottom of the hill? And I think the thing that will help us draw better tangent lines as we do that is to think about if I was walking along this hill, or if I'm a ball rolling, or whatever the case may be, if I really freeze time and I pause myself at this moment, like, where am I looking if I'm going from left to right? And letting myself like tilt like with the mountain, like if you're on skis or like snowboarding or something like that, like I'm not going to look down at my skis because I'm going to trip soon. I'm not going to look up at the sky, although it's pretty. Like I'm going to look out in front of me. I'm not going to look directly out in front of me so I can really experience the whole view. And I want you to kind of have that feeling too, that as you make your way, what's going to happen is where you're standing kind of adjusts your sight line a little bit as to where you're looking. Right, and those arrows that I'm kind of drawing right there, like that gives you a sense, hopefully, of how the tangent line is going to change with that. Can you see that? Can you kind of like picture what I'm talking about? Now, however that fits for you, walking up and down a mountain, rolling a ball up and down a hill, like riding on a roller coaster and being in the first car and like, I'm just going to look straight out, whatever direction I'm pointing, that's the direction that I want to draw these tangent lines. It's just that I'm not here. I'm infinitely small and I'm just hanging out on the line itself. And so when I try to do what they're doing, which is estimate the derivative at something like -7, right? Where they say, okay, stop right here and see if you can figure out what the derivative is, which is just the slope of the tangent line. That, hey, if I can draw that tangent line really well, I could probably estimate it pretty well. Now, here's my best advice in drawing these tangent lines, okay? Of course, if I draw a tangent line right here, that has to be a point on this line. But for me, I'm going to try to make it the only point that runs into this function as best I can. But if I want to estimate that number to be nice, we're going to pick pretty nice numbers. The easiest way for me to deal with slope, which is the change in y over the change in x, is to make that distance just 1. I'm going to try to go just 1 box to the left or to the right, or both. And I would love to make this an integer. I want to just go up and down a few boxes, however many boxes I'm supposed to do. And so when I graph this, I try to look for where my next point might be on this tangent line. Of course, it's not going to be on the function. It might be a little bit above or a little bit below, kind of depending on what things look like. But when I graph it, I'm going to try to graph it in such a way where I can find another point that is just 1 box away, left or right, and lands nicely on a grid line somewhere, as best I can. Now, these are just estimates for sure. But when I think about trying to like graph this tangent line well, and I just kind of go like this, pretty small, if you don't get yourself at least a box to the left or a box to the right, it might be hard to estimate that well. Because when we talk about slope, it's just rise over run. If I just make my run 1 box over, let me try to land nicely somewhere. Because look at that line. What do you think that slope might be? 4, 3, 2, 5, like something, right? Something like that. But it can be kind of hard to do if you don't actually like go and hit another nice point somewhere else so that I can count. Oh, I went over 1, okay? And then I went up 1, 2, 3. As simple as that might seem to like try to use like an algebra 1 kind of like slope mindset, and saying like, I'm going to go back to it, but like, I think that derivative might be 3 or 4 or 5. If I actually draw this out as best I can and try to hit that next point, I feel like we'll just do a better job at making that estimate. Do we feel okay with 4? Does that seem pretty good? And if you said 3, it'd be hard to argue with you. I think it's pretty good too. I don't know about something like 2 though, because like actually draw a line through that point that has a slope of 2. That's like up 2 over 1. That's that line right there. And that just doesn't feel as nice, right? That doesn't look tangent. Now, how many times do I hit that function right around that spot? Yeah, just 1, I know. But the idea is that that line represents way more than just like, oh, the tangent line. It's what direction is that point moving at that moment in time? And I think that mindset is going to help you wrap your heads around calculus a little bit better. Slope of the tangent line, sure. No. Direction of movement. What? am I looking at? If I'm sitting on that point and I'm like resting on the function and kind of like looking in that direction, where am I going? Does that sit okay with you guys? Okay. Now, if that's true, if we are a point moving along this function, or you're walking up and down this hill, or however you want to think about it, what do you think? Look at the next column over. Is the function increasing, decreasing, or are we at a relative extremum at that spot? Well, when they say is the function, like, am I? As I walk along this path, am I going up? Am I going down? Or did I hit a peak or a valley? Well, what do you think? If you're right here, in that moment, what are you doing? Are you increasing? Are you decreasing? Are you at a relative max, or are you at a relative? Going up, right? I am literally walking up this hill because I move from left to right. Now, that left to right movement, I think, is going to help us out. Let's just say that we are increasing in I, and C is an I. Okay, increasing and decreasing in long enough words, we're just going to read. And we're going to leave that whole last column blank with the whole equation of a tangent line. You guys know how to find the equation of a line. I'm more worried about making connections between derivatives and the kind of the movement of the function. And so then we try it again, right? I try to draw a tangent line at this next spot as best I can, but I draw it in a way where I try, if I possibly can, to hit like another nice point above or below the function, like whatever kind of feels nice with that tangent line. So I can estimate that derivative to be relatively nice, trying to avoid fractions and decimals if I can. Of course, they're going to come up, but if you can avoid them, even better. So what do you think? What do you think that derivative might be at that spot? 2. Yeah, I feel pretty good about that being 2. And the steepness of that line, yeah, it's not nearly as steep as this one was. We tried to draw that tangent line right there. And so if I'm taking a walk up this hill, man, if I stop at that first point, I'm really like having to push myself to take that next step. I'm increasing a lot faster. A lot harder for me to take that next step. But as that tangent line starts to level out, it gets a little bit easier for me to do. But are we still going up at that point? Absolutely. So let's say increasing as well. I'm going to stick with the same color scheme. Okay. What about at -4? What is the tangent line going to look like at that point sitting on top? Perfect. Absolutely. Horizontal tangent line at that spot. Right? But imagine yourself like you got to the top of that hill. Like, where are you looking? If you're just looking like in the direction your body is facing, you are looking straight out. You're not looking down the hill because you haven't looked down yet or up at the top. In that moment in time, you've reached the top. Where am I looking? I'm looking straight out. Right? I'm looking at the whole distance in front of me. So what's that derivative? What's the slope of a horizontal tangent line? Now, is that point a relative minimum or max at that spot? We're a max. Okay, and MAX is good. Awesome. Okay, now though, we take a couple steps and we start making our way to the right, right? Because we're always going to move from left to right. Drawing this tangent line right there, what do we think that slope might be? Now, if it was -2, I would literally like hit the function again right there at that very next point. So I think -2 might be a little too steep. Yeah, -1 looks pretty good, right? I can kind of draw a line that just goes like down 1 over 1. So I like that. I think saying, hey, once we get to -2, yeah, we're at more of a -1 kind of slope. And what do you think? Increasing, decreasing, min, max? Sorry? Yeah, going down, absolutely, right? You're walking down the hill. And that mindset for me, rolling a ball or pushing a rock or actually climbing a mountain, whatever you think of, I think that helps a lot. Okay, so we were right there. All right, let's draw the next one at -1. Now here's the thing though, I'm gonna blow this up a little bit so you can see it because this happens, it's okay. When I try to draw a line tangent to that point right there, like that. If I draw it too flat, obviously I'm going to run into the function over here, right? But if I draw it too steep, I'm not really looking down like that, right? Like imagine, all right, here I am hanging out over here. Like I feel like I'm just kind of pointing myself down in that kind of direction. How are we going to draw this line as best we can? And think of like all of these lines, all of them existed above the graph, right? All of those lines existed like above the graph itself. I think we get to this point here where the best version of this, like this line is this curve is at its steepest at this point. It's okay that your tangent line like cuts through the points like that if you feel like that's the best. Because I don't know, if we drew it any other way, you draw a line that kind of looks like that, like I have to like kind of curve it for it to really stay above the whole time. And so what I'm trying to say is we talk about slope of the tangent line, and that's really a good way to start thinking about it. But I think what's most important is that we realize that that's just one nice way of thinking about it. Where really you just want to draw the direction that the object is moving at that point in time if we were rolling it smoothly along the same. So I don't know what's best. We're just going to try to do the best we can. What do you think? What do you think that slope might be at that point? -2? Sure. I think that's a good estimate. I also think -2.5 or -3. I think we've got some choices there as to what's perfect. And so I'm not stressed about actually being perfect, but clearly we are still going down. Right? We are definitely and down. All right, what's happening at 1 there? What do we got? What's our tangent line look like at the bottom of that hill? Perfect. Slope is 0 again. Okay, so I'm going to switch colors, go back to this one. Eventually, we'll put this all together. And there's a minimum, right? We are at a relative minimum at that spot. Okay. What about at 3? What do we think the slope might be as you draw a line tangent to this point? And I think this line might be like completely underneath the graph at that point. That's okay. What is that slope? 2? Sure. 2, 3, maybe. Yeah, that's okay. I'm going to go back to the blue because now we're increasing again. 2, increasing. And zoom out like this here. That's more than here. There, it's better. And then what's the last one? We got a point there at the top. What's that at 5? We back to 0 again. Yeah, okay. So back to 0. Okay, and that's a max. And then over the hill we go, and down we go really fast. Looks like we're taking off. That might be, yeah, -3, -4. Sure, whatever. Either one's fine. I feel like I'm all over the map with what I'm writing where, but yeah, -4? That's something. Again, it's just an estimate. And while that whole process is nice to go through, it's really about what we're looking at. It's about this. It's saying, okay, this is all I have now, right? Cover up the function. I don't need it. I have this that says, okay, here's the derivative at a whole bunch of spots along the way. Is there anything kind of overarching, or are there bigger, more general conclusions that we can make about the value of the derivative at a spot along that function and what it might mean with regards to what's happening with that? If that function is the ball rolling up and down a hill, what does the value of the derivative tell me about what's happening as that ball is rolling, without me actually having to watch? So it could have relation to speed, right? The bigger the number, the faster it's moving. Absolutely. This is rate of change. Derivative is absolutely rate of change. So speed is a great way to think about it. What did you say, Ellen? Okay, so not only about what speed, because speed is the absolute value of velocity, but up versus down, right? And so what tells us the difference between whether the ball is rolling up the hill quickly or rolling down the hill quickly? The sign. And that's a big takeaway that we're going to start putting together, is that while the numbers are very nice to know for sure, what we start with initially is the sign of the derivative changing from being positive and that telling me that we're increasing to negative, where the function is decreasing, or where we're at 0 with the potential of a relative extremum. Now, and so, but in order for there to actually be a minimum or a maximum, so, you know, like here and here and here, what do you notice about what's happening before and after that slope of 0? Because slope of 0, very, very important. If I want to be at a relative minimum or max, it has to at least have a slope of 0. But some other things kind of have to happen along the way, and then after the fact to get us. So when the function is increasing, things are positive, but as we approach a maximum, I better start slowing down to do that. And you can kind of like see the, like if my hand represents the tangent lines as we're moving, right, pretty steep, like a slope of 4, to a slope of 2, to a slope of 1, to a 1/2, to a 1/4, and eventually I have to get to that 0. Okay, so the numbers have to start kind of moving towards 0 for that to happen. Okay, good. Especially if we have this really nice smooth graph like that. Okay, graphs that have sharp turns are not as nice in calculus. So we like the ones that are not just continuous but smooth and rounded. Good. What else do you see kind of happening on either side of a 0 in order to create an actual minimum or a maximum along the way? Notice any other trends in the numbers? I like that one. Okay, they're increasing like in the negative direction. Well, let's see. So if I'm heading down towards a minimum, I think it just might be because we're kind of far away. I think if we checked some derivatives in between, you'd see that the same trend was happening. If I'm going to go towards 0, I better actually take a turn and start flattening out to get there. So yeah, -2, but it might go like -2, -1, -1/2, negative. I think we'll have to actually get towards 0. I think this might be a little misleading because it goes -1, -2. Only because we're not looking like here and here and here and here and here and here. Right? The limit is getting closer. We want to see what's happening. And I think as we went slower, and I think like that point is like one of the fastest where it's going down. But you would see that the tangent lines would start to flatten out as we approach that spot right there. What else? Do you notice anything else about kind of the flow from top to bottom? Yeah. Signs are changing. Oh, okay. So as we look on like either side of a maximum, the slopes went from positive to 0 to negative. But well, think about that. Like, look at the trends in my hand. If I want to hit a maximum, I better go up, hit it, and then come back down. The only way for me to create a relative maximum is to go through this motion, right? I got to go up, hit it, and then come back down. Which means that the slopes of my tangent lines are going to do just that. They're going to go from positive to 0 to negative. Because if I go in any other way, if I don't switch signs on either side of that maximum, then I'm going from a graph that is increasing to 0 and then increasing. Like the slopes of these tangent lines go from positive to 0 to positive. And well, yes, for a brief moment right there's a horizontal tangent line right at that flex. Is that a relative minimum or a maximum? No, that's not the highest or lowest point in the space nearby. That's just kind of like a, I made it to a clearing in this hike, but I still have the rest of the mountain to keep climbing. And if we don't see the change in the signs, right, if we go decreasing to 0, slope of 0, to decreasing again, right, if our slopes go from negative to 0 to negative, we're not actually hitting a relative min or a max. So it being 0 at a point is a great start, but we have to see that sign change on either side from positive to 0 to negative. That's the only way to do it. Go up, hit it, come back down. Or if I want to hit a relative minimum, I better go down, hit it, and then come back up. Right? My slopes have to go negative to 0 to positive. And so as nice as it is to find these critical values, right? These spots where the derivative is equal to 0, look, positive to negative, negative to positive, positive to negative on either side, right? And so that's kind of the big takeaway that we start with early on. So go ahead and turn the page. Now, once we start making connections to the fact that the number itself represents actual steepness of the line, so speed, or in a better sense, velocity, because velocity happens in positive and negative directions versus, so up and down and left and right. Those are two different directions. What we can start to do is say, you know what, in general, the sign of the function derivative tells us something about the function itself. And so I think a great way to organize this would be to say, load up a little bit so I can write bigger. Ooh, would be to say something like, okay, if that if this is true, then I know something about this. And if that's true, then I know something about that. Like if I know for sure that f prime of x is positive, so I'm just going to say greater than 0. What does that tell us about the actual function itself? Then f of x is, or an object moving along that function, we're increasing, absolutely. And I'll write out the whole word this time so we can see it, but you'll see I'm just going to always, almost always, abbreviate INC and DEC. Increasing and decreasing. Right? And now we can, like, oh, there we go, nice. So I know for sure. Find the derivative, right? You give me a function, and I find the derivative, and I stop at a point, and sure, it's 5, or it's 3, or it's 12, or whatever. It's positive. If the derivative is positive, my function has to be increasing at that point. Okay? If the function is negative, if the function's derivative, excuse me, if f prime of x is less than 0, then the function has to be decreased. There it is. But if it's actually 0, right? We pick a moment in time, and we actually stop somewhere, and we say, all right, let's plug in this x value, let's see what we get, and we actually get 0. Is it guaranteed to be a relative minimum or a maximum? Not necessarily, but it could be, right? And that's kind of a really good first step, that f of x might have a relative extremum. It might. I would love it to, but it might not. Right now, what do we need to be true kind of on either side of that 0? If we want to know if it's a max or if it's a min, what do we need to have happen to the derivative if we want that actual relative extremum to be there? We need the sign change. Good. What we need, a sign change in f prime on either side. Let's say that. Okay. If we don't have a sign change from the derivative around the 0, then it's not going to be an extremum. It's just going to be kind of like a landing point, a quick plateau as we kind of continue to increase or continue to decrease. And it's nice that that kind of flows naturally and it's intuitive. Yeah, question. So these, all of these points are actually, I alluded to it, they're called critical values. And we'll formalize that name sooner rather than later. But any points where the derivative of a function is 0, that x value is called a critical value. But a point where the sign of the derivative doesn't change is not a relative minimum or a maximum. But there is another thing that's happening that, and so this is chapter 4 that we're kind of getting into. So jumping the gun a little bit. But you can kind of consider if you broke up this function in spots where the derivative is at its steepest. So not where it's 0, not these points here, 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 and here, but the points here, 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 where the slope of the tangent line is kind of the steepest in the space nearby, whether it's steepest in the positive or negative direction. What you see is a change in something called concavity. And this is the chapter 4 idea. But it talks about the difference between whether you've got something that you can fill with water or something where the water would roll off the top. Something that you can fill with water if you put it in the middle, or something where the water would roll off the top if you put the water on. Like imagine like dropping a droplet of water inside. Would it fill if I kept doing that over and over again, or would it start to spill over the edges? And so these points right here, so this point, and this point where concavity changes, those are called inflection points. And again, we're getting ahead of ourselves a little bit, but hey, why not? Let's talk about it. Those inflection points can happen there, right there, by looking at half of these graphs. A half where if I were to kind of continue, well, I'd kind of go like that, right? And so the inflection happens, okay, this cannot be filled with water compared to this. Like if I just kind of continue that trend, that other half of the graph would go up like that. And so what we're looking at are two kind of sections of this graph, one that is concave up and one that is concave down. And so what you'll see is that at this point right here, the derivative is 0. Getting ahead of myself. The second derivative is not. And we'll talk about that. Okay. Inflection points is what we're getting to. But that's chapter 4. So let's deal with first derivative, simple stuff first. By having this understanding that the sign of the derivative tells a pretty nice story about what we're looking at. And by skipping this whole bottom of page 124 and jumping right to 125, we can start to put this idea together by saying, all right, look, I know we stopped at a lot of like individual points along the way. Now let's see if we can find entire intervals where all this stuff is kind of happening. Okay, and can we like almost kind of like widen our gaze a little bit and say, hey, okay, if you want me to know where the derivative is negative, really what I'm looking for is where the function is decreasing. And that's the story that I think you need to tell yourself and make sure that you're okay with that kind of connection in your mind. That if then that we just wrote down, that if the function is has a derivative and that derivative is negative, what I know about the graph from left to right, and that's very important. We're going to read these graphs from left to right. but the function is decreasing in that section. And we're going to look for entire intervals. And when we talk about intervals, we're always talking about x intervals. Right? So values of the domain where this is happening, because we're talking about the y values getting smaller. So I don't have to do y intervals. We're just looking for x intervals. Where as I read this graph from left to right, the graph is decreasing. Really, I'm walking down the hill, right? I let go of the ball and it rolls down it. Whatever you want to think about, kind of, this section right here, that is the section where as I read it from left to right, my eye gaze goes down as I move along the function. So all the way between -4 and -2, those are the x values, right? I know they're giving me the y values. That might be unnecessary information given the question, and they like to do that. But all the way from -4 to -2, this graph is going down. What about actually at -4? Are we going down yet when you're at the top of that hill? No, so I can't include that endpoint, right? What about at -2 when you finally actually reach the bottom of the hill? Are you still going down when you get to the no, right? So absolutely not. We can't include those endpoints when that happens. And you're going to see that's going to be true all the way through, okay? When we talk about these intervals of increasing and decreasing, they're going to be open intervals because we have these spots where the slope is 0. Is there another section of this graph where it's going down from left to right? Yeah, absolutely. Well said. From 1 to infinity. Okay, so we're going to put a little union here, and let's go from 1. And, maybe a graph just has one section like that, or it has 2, or it has 3, or whatever. Usually don't know more than that. That's enough. Or maybe none, right? The graph doesn't have to go down at all, right? I drew this graph for you. But I drew this graph for you. That graph is never decreasing, ever. There's not going to be a single x value where the first derivative is negative, and that's okay. That's just part of what we're looking at. Okay, so now they want a positive derivative. So what I'm looking for is where this graph is increasing. That's what I want. And when I see that statement, right, g prime of x is positive, in my mind, I'm like, okay, I want the slope of my tangent line to be positive. Okay, what am I really thinking about? I'm thinking about movement that takes me up the graph. And start from the beginning, right? All of that right there, I feel like that, that has a positive slope right there. All of this right here, that all has a positive slope right there. There's where it's negative. There's where it's negative. But, let's go from negative infinity all the way to -4, and then let's go all the way from -2 to 1, right? All of those sections, the graph is increasing as we go. So we read it from left to right, and I'm walking up. And although this last line, right, g prime of x being equal to 0, I would love it to be a min or a max. It doesn't have to be. I'm just looking for those horizontal tangent lines. Either where, maybe I am at a minimum or a maximum, or maybe I'm at one of those inflection points where concavity changes. But we'll get better at kind of spotting those as we go. I still need a horizontal tangent line. That's what really this is saying. Okay, when I see the slope of 0 is a horizontal tangent line. Okay, that's my mindset. I don't want to say relative extremum because it might not be, but no matter what, it definitely has a horizontal tangent line. And you can see intervals in blue, intervals in red. Now it just says the values of x. These are going to be points in time, usually, because we're talking about like smooth and rounded curves, not a whole lot of constant sections. What are those x values where you see a horizontal tangent line? -4 for sure, right? Boom, right there, okay. Anywhere else? -2, definitely, are down here at the bottom, cool. And 1. Yeah. And just like that, it's fine. You want to get a little fancier? Don't need it. It's okay if you don't. Does it sit pretty well with you? Can you kind of visualize things well enough in your mind to go increasing, decreasing? Okay. All right. if that sits pretty well with you, then we'll have a really good chance that the next couple chapters go really well. So that's really good. You need those ideas to kind of sink in and really kind of be part of your calculus definition in your mind. And what's really at the heart of this is movement and change and like watching things happen and kind of experience them in 2 dimensions while we're kind of taking that path. So cool. If you're good with that, I'm good with that too. I just have one quick thing to interject. I'm not sure that it fits anywhere really nicely in any of these chapters, so they just kind of stick it in now that we're getting more comfortable with it. And I'm only going to very, very, very briefly touch on the normal line. And seriously, it's just this right. And for right now, that's all I'm going to say. Okay? We talk about tangent lines, right, only hitting the graph once. The normal line, and that is a capital N normal, okay, that is the official name for this line, is just perpendicular to that instead of tangent. Okay, so if I draw a line, let's say like -3, like okay, like here's my tangent line at -3. Okay, so there's my tangent. Okay, the normal line is perpendicular. That has a lot of applications in physics, in a lot of different ways that I will save for when the time comes. But basically, here's a really good example. Like, here's a mirror. I'm going to bounce a light off it and watch it reflect. Okay, there's my point of tangency. The normal line is the line of symmetry. It's the line of reflection. So, lot to do with the way that light moves. But normal line is perpendicular to tangent line at that. That's all I really need from you right now. Okay, so put that in the back of your mind. We will come back to that another time. But let me just get you started on thinking about this next page. We did it. We made it. I got us to page 126. I wanted to at least get here. I don't think we'll finish it, but that's okay. Look at this graph. What do you see? You see anything? Can you break this down at all? Can you tell me about what we're looking at? There's what? 2 extremas. Nice. Right. We've got this spot right here. We got a relative max. We got a relative min. Cool. Anything else about this graph that you think is nice for us to know before kind of jumping into the table at the bottom and trying to answer some questions? Got 2 extrema. It's got a few x-intercepts, right? We got this spot right here and this spot right here, right? We got 3 x-intercepts. Cool. Yeah, it goes up, goes down, heads back up, right? What is this the graph of? Looks cubic, right? Nice. It is. This is some cubic graph. But what does that cubic graph represent? Okay. This is not the graph of a function. This is the derivative of some function. So when I talk about like that being the max and the min, that's not the max and the min of the function. That is the maximum and the minimum of the derivative. These spots right here, I know we're going to run a little short on time. Like those spots right there are where the derivative is 0. Not where the function's 0. That's where the derivative is 0. Those are your potential extrema. -2, 1, and 3, not -1 and 2. Give me a second. Okay? All of the space up here, all of the space above the x-axis, That's where the function's derivative is positive. Not where the function's going up and then down and then back up. No, that's where the derivative is positive. All of this space, all in there. Down here, where all of this, where the derivative is negative, not where the function's negative, where the derivative is negative. And so we got to be really careful reading what they're giving us, because now we're going to go the other way. They've given us a graph of a function. Cool, we can talk about the derivative. Now they're giving us the derivative. And now we're going to make some assumptions. We're going to make some conclusions about the actual function. Okay, so we'll come back to that right there. We'll pick that right up tomorrow. Okay, nothing you have to submit for me today. Probably nothing you really have to do too much of submitting this week. Let's just come back tomorrow and we'll keep going. Awesome. Thank you guys. Have a great day. I will see you mañana. Last week before spring break, and then we are back.